Okay, welcome back to the next video. What we're going to be covering today is just finishing up question 6 and question 7 from the back of your textbook. So this one takes a little bit of mathematical skills to kind of solve. It's just remodifying an equation or interpreting an equation, because remember we've got our delta G equals delta H minus T delta S equation. So basically the importance of this is just being able to interpret this equation. So it says, okay, explains in terms of delta G why a reaction which both delta H and delta S values are positive can sometimes be spontaneous and sometimes not. So with this, right, you can think about this in multiple ways. So delta H is positive, which means that it's endothermic, and delta S is positive, which means that it's increasing entropy, which we know is something the universe wants to do, increase in entropy. So we know that an endothermic reaction, right, this requires heat. So it's just like, back when we did that equation on equilibrium, if we increase the temperature of an endothermic reaction, you push it to the right. You push it to the product side. So you can kind of think about this in that same kind of way. So this reaction is endothermic. So if you want it to produce more product, if you want it to be more spontaneous, we need to increase the temperature, and that's what interpreting this equation does. It's our Gibbs free energy is it's endothermic, so it requires temperature, but we are supplying some sort of temperature to the system that also depends on the entropy of the system. So let's say Y can sometimes be spontaneous and Y can sometimes not. Is that it depends on the magnitude. So spontaneity in this case, spontaneity, another way is saying delta G, is dependent on the temperature of the system. Because, right, if we've got a very, very low temperature system, if we were to do this calculation, let's say delta G equals delta H minus T delta S. If we were to do this equation, right, this is endothermic, so this is I always like to put numbers to it. So we'll just say 1,000. So it requires 1,000 kilojoules of energy. But then we're doing the reaction at a low temperature. So we'll say we're doing it at 0 degrees Celsius, but the delta S value is only we'll say 1 kilojoule. So right, we've got room temperature, and we release 1 kilojoule of energy in terms of entropy. So if we were to do this equation, right, we'd still have a positive value. Delta G would still be positive, which means it's non-spontaneous. But it makes a little bit of sense, right? We raise this all of a sudden to, we raise the temperature of the reaction to, now we have to do it to 1,000 degrees, or 1,000 Kelvin, so a few hundred degrees Celsius, 600-700 degrees Celsius. You can see that, right, this value would start to become negative, and if it's negative, it's spontaneous. So that'll be our description for why it's sometimes spontaneous and sometimes not. That spontaneity is dependent on the temperature of the system. The higher the temperature, the more spontaneous the reaction becomes. So as we increase the temperature, we offset this endothermic process. We offset it by basically not increasing the entropy, but increasing the multiplication factor of the entropy, of the positive entropy change. Okay, so let's go to the next one. Hopefully that one made a little bit of sense. The next one, throughout this question, use relevant info from the data booklet. So again, right, the question's telling us right here, data booklet, so we know that is required for this question. So at least it's telling us to use our data book. So define in terms of delta H of define the term delta H of formation, the enthalpy of formation, and illustrate your answer with an equation, including state symbols for the formation of nitric acid. So delta H of formation, remember it was the enthalpy change for the formation of 1 mole of product from elements in their standard states under standard conditions. And standard conditions is typically 25 degrees Celsius and 1 atmosphere of pressure. Because if we start to change the pressure, we start to change how things react. And if we, as we just saw, if we increase the temperature, we also change how things react, right? In an exothermic process, we increase the temperature. It may not necessarily help with it. It depends whether it's at equilibrium or not. So okay, the enthalpy change, so the delta H of formation is the enthalpy change for the formation of 1 mole of product from elements in their standard states under standard conditions. So I'll explain this more once we've done. For those of you who already understand this, I'm going to do the answer, and I'm going to explain this definition through the answer. So we're forming nitric acid. So let's look at what nitric acid is. You should all know this equation for nitric acid at this point. And nitric acid is a liquid at room temperature or under standard conditions. So HNO3 is nitric acid. So HNO3. So what we need to do is we need to figure out what elements can react to form nitric acid. And it's hydrogen. And we know hydrogen is a gas in its standard state, right? We find hydrogen in its elemental state is H2. And it's a gas under standard conditions. It's a gas at room temperature and 1 atmosphere of pressure. We know nitrogen is the same thing. Because right, we're breathing in nitrogen right now in air. And finally with oxygen too. Oxygen is the exact same thing. So now we've got hydrogen, nitrogen, oxygen, all in their standard states. How we would find them in nature, H2, N2, and O2. And in the gas phase, because it's at room temperature and 1 atmosphere of pressure. And then the difficult part, right? The difficult part is, or this is the important part, it's 1 mole of product. So it doesn't care about how many reactants, but we know that this number needs to be 1. We can't have this number be 2. It needs to only ever be 1. So now we need to start balancing this. Okay, so we need only 1 H. So in order to balance this, we need half of this, right? Half of 2 hydrogens is 1 hydrogen. 1 nitrogen, half of 2 nitrogens is 1 nitrogen. There you go. And then finally, we need to turn this 2 oxygens into 3 oxygens. So we need to multiply it and then divide it. So we need to multiply it by 3, divide it by 2, and we'll have 3 oxygens. So okay, hopefully that makes a little bit of sense. And that's how we think about it, right? Standard state. Standard state, what it means is that it's how it's found as an element, how it is found in the most abundance in nature. So it's how it's found in the most abundance in nature. Okay? Then we've got the next one. This one is, right, we haven't used our data booklet yet, but it says you need your data booklet. So okay, so let's look at these equations. Propyne undergoes complete combustion as follows. Here's the equation. Calculate the enthalpy change of this reaction given the following additional values. So it gives us the values, but what we need to do, right, we need to think this is the delta H of formation. So this is just like our Gibbs free energy of formation. We need to use that same type of equation. So if you were to remember that equation, right, our delta H formation of the reaction is equal to the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. So it's products minus reactants, right? This is the same equation, kind of the same equation we used when we calculate the bond enthalpies, if you guys remember the bond enthalpy calculations. So it's similar to this, products minus reactants. So let's look at this, the delta H of formation, products minus reactants. Let's see which ones are products. CO2 and H2O are products. And remember, it's kilojoules per mole. So here we've got 3 moles being formed. And of H2O, we've got 2 moles being formed, so we need to multiply by that factor. And then we've got propyne right here. Propyne, right? C triple bonded to C, C, H, and then 3 H's. For those of you who haven't covered the organic chemistry unit yet, or didn't do IGCSE chemistry in advance. So that's propyne. Ine, right here, means that there's a triple bond. And that's it, just means that there's 1 triple bond. So okay, so let's do this calculation. So delta H of formation is equal to the sum of the products. So the sum of the products is negative 394 multiplied by 3. So that's our delta H of formation of CO2 times the molar coefficient, plus, and we had to add negative 286 multiplied by 2. And we have to minus off the delta H of formation of the reactants. And you can see that we do not have that given to us here, so we have to go to our textbook. You check this, selected compounds, thermodynamic data, delta H of formation, conveniently supplied right here. We scroll down, propyne is right here. Delta H of formation is 185 kilojoules per mole. So the delta HF naught of propyne of C3H4 is equal to 185 kilojoules per mole. So minus, there's no coefficient here, minus 185 kilojoules per mole. And let's solve this one. So I got to get my calculator out right now. So we need 3 times 394. So here we got negative 1182. Negative 1182. So I always like breaking down this calculation, right? We could do this all at once in the calculator, but you're more than likely to make a mistake in your final exam if you do that. I prefer doing it part by part by part, because then you could really focus on the numbers and the numbers making sense. If you type this all into your graphical calculator and hit enter, it spits out a number. You know, it's harder to double check. So plus, let's check the next one. 286 times 2 is negative 572. Negative 572. And then minus 185. And now let's try to break this apart. So this is a minus, plus a minus, minus another one. So we can just add them all together and throw a negative sign in advance. So 1182 plus 572 plus 185. Our final answer should be negative. Remember to make it very, very clear for your teachers, delta HF naught of reaction. The clearer you are, the easier it is to mark, is equal to negative 1939, equals to negative 1939 kilojoules per mole. And always, like I said, I like the final answers either highlighted or circled. So that is our final answer right there. Okay, let's go down to the last one. Explain why the delta S for B would be negative close to, or why the delta S for B, if that's better, if the delta S for what we just solved would be negative close to 0 or positive. Let's just look at the equation. Let's just observe this equation. Right, so remember, we need to count moles of gas, matter, and phase changes, matter. So before we've got 5 moles of gas, after we have 3 moles of gas, and 2 moles of liquid. We can see already, right, this is more disordered. This is in liquid phase, so it went from a gas to a liquid. So that is a gain in order. So it's the entropy decreases. And then you know that the universe hates the entropy decreasing. So the entropy is decreasing, so that's a bad sign. And we've lost moles of gas. So let's scroll down to the bottom and let's see. With the delta S, is there more disorder? Remember, delta S is a measure of disorder. So is there more disorder, less disorder, or the same amount of disorder? And we went from 5 moles of gas to 3 moles of gas and 2 moles of liquid. So that to me looks like a decrease in disorder. Therefore, our delta S is negative. And that's what you need to supply in your answer. Delta S is negative. Why? Because we're going from 5 moles of gas to 3 moles of gas and 2 moles of liquid. We are gaining order. Gaining order. Okay, so that's all the questions for the end of the chapter. I will see you soon for the start of chapter 6. Thank you.